For cations occupying tetrahedral void, so R plus by R minus is 0.225. And for cations occupying octahedral void is R plus by R minus is 0.414. So radius ratio is very important for determining crystal structure and coordination number. So radius ratio, if it falls between 0.155 to 0.225, so possible coordination number is 3. The structural arrangement will be trigonal planar. For example, B2O3. When radius ratio falls in the range 0.225 to 0.414, the possible coordination number is 4. Structural arrangement will be tetrahedral. Examples: copper CuCl, Q plus chloride, Q plus bromide, and Q plus iodide. When radius ratio falls in the range of 0.414 to 0.732, so possible coordination number is 6 here, and the structural arrangement will be octahedral here. Examples: sodium chloride, magnesium oxide, calcium sulfide, etc. And when the radius ratio falls in the range of 0.732 to 1, possible coordination number is 8, so structural arrangement will be cubic. Example: cesium chloride, ammonium bromide. Next, lattice energy. So lattice energy is the amount of energy released when 1 mole of an ionic solid is formed from its constituent gaseous ions. So next we discuss Born-Haber cycle. From here actually we can calculate lattice energy. Okay. So Born-Haber cycle uses Hess law. Hess law we study in thermodynamics. So Born-Haber cycle uses Hess law and states that the enthalpy change of reaction will be same regardless the path it takes. Okay. So this is typical example of Born-Haber cycle. So what are the steps here? Okay. So first step is sublimation, where sodium solid goes to sodium gas, and for this process delta H, or enthalpy change if we call delta H, sublimation. Okay. So we go back and check the figure. Okay. So NaS, sodium solid, goes to sodium gas. Okay. So this is for this change the value of delta H is delta H sublimation here. Then what we need to do, because this is Born-Haber cycle of sodium chloride, so we need to first create Na plus, and then we have to create a Cl minus, and then we get NaCl. So next is we have to ionize Na gas to Na plus, right? So next step is, okay, here next ionization of Na. So Na gas goes to Na plus gas plus electron. So this is your ionization energy. Okay, here for sodium. So for sodium it is done now. Now for chlorine. Okay. So for chlorine, first chlorine is present as is a diatomic species, right? So atomicity is 2 here. So Cl2, from Cl2 to Cl2 we have to get Cl minus. So we start with half Cl2, right? So it gets half Cl2, and then we have to dissociate, right? We have to dissociate. So we have to get, so Cl2 is present as gas here, gas. So we have to get Cl2 to Cl gas here. So for this process the change in enthalpy is delta H dissociation. So this for chloride. So next we need to consider dissociation of chlorine. So you get half Cl2 gas to goes to Cl gas, and for this process change in enthalpy is delta H dissociation. Okay. Next what we need to do? We need to next Cl gas we got. Okay. So we have to get Cl minus, right? So so this Cl gas, it has to gain an electron. Okay. So that's why this electron affinity is there. Okay. So once we take for this process Cl gas to Cl minus, this is called electron affinity. So Cl gas to Cl minus gas, Cl gas to Cl minus gas, we get electron affinity. Now what we got? We got Na here. This is also in gaseous state, and Cl minus, this is also in gaseous state. Now we need to add them, right? So lattice formation is taking place. Na plus gas plus Cl minus gas gives to NaCl. Okay, and this is the energy change here, U. Okay, so here you can see Na plus that is your U is lattice energy. So Na plus plus Cl minus gives NaCl, and this is the lattice energy for this. Okay. Now how we can calculate lattice energy? So total energy, if we see, so according to Born-Haber cycle, so delta H naught F, so enthalpy of formation, change in enthalpy of formation is, what are the steps involved here? So delta is sublimation, right? So delta is sublimation. Next, delta is dissociation of chlorine, that is also there. Then ionization energy of from Na plus Na gas to Na plus gas, this is there, right? Then we got chlorine gas, we have to get chlorine Cl minus, so electron affinity term will be there, so plus electron affinity, and then once we get this, so Na plus and Cl minus, it requires this is lattice energy U, okay, so plus U, okay. So all these things will give delta H naught formation of NaCl, okay. So this is Born-Haber cycle. Then we discuss isomorphism, a phenomenon where two or more substances can have same crystal structure is called isomorphism. For example, NaNO3 and CaCO3, ZnSO4.7H2 and MgSO4.7H2. Conditions for isomorphism: for polar molecule, comparable chemical formula, NaNO3, CaCO3, right? Comparable chemical formula. Same chemical and geometrical arrangement of ions. Size and polarization of ions must be similar. For non-polar molecules, should not have major difference in molecular volume and similar chemical constituents. So these are the conditions for isomorphism. Next we discuss heat capacity of solid. So Dulong and Petit law. At room temperature, the heat capacity of most solids is around 3 kb, okay, 3 times Boltzmann constant per atom. So molar heat capacity of n mole of solid is 3n times R. So for every atom it is 3 kb, right? So for 1 mole, so for 1 atom we get 3 kb, right? Heat capacity. For 1 mole we get 3 times Na times Kb. Na is the Avogadro number, Kb is the Boltzmann constant, Kb Boltzmann constant here, okay, and Na is the Avogadro number, okay. So Na times Kb gives 3R, so this is for 1 mole, and for n number of moles we get 3nR, right? So that's what. So at room temperature the heat capacity of most solids is around 3 kb, or K or Kb is the same. So K here is the Boltzmann constant per atom. So molar heat capacity of n mole is 3nR, or R is the gas constant, okay. Here R is the gas constant. So you see that for according to Dulong-Petit's law, the heat capacity of solid is constant, right? So this is 3nR. Next we discuss Einstein's theory of heat capacity. In solid translation or rotation of atoms is not possible, okay, but vibration is possible, okay, because atoms are in solids, they can only vibrate, okay, they can only vibrate, but rotation and translation, okay, these are not possible. So Einstein treated the atoms in a crystal as n simple harmonic oscillators, all having the same frequency nu e, where nu e is called the Einstein frequency, okay. So nu e is the Einstein frequency. The frequency nu e depends on the strength of the restoring force acting on the atom, that is the strength of the chemical bonds within the solid. N atom solid is equivalent to 3n harmonic oscillators. This treatment is a gross approximation, since in reality the lattice vibrations are very complicated and coupled oscillations. They are not independent one, okay. The energy level of the harmonic oscillators are given by, so for this is for simple harmonic oscillator, the energy is EV, if we say V is different vibrational energy level, okay. So EV is h nu times V plus half, okay. So this is for this is the energy of one harmonic oscillator, where V goes from 0, 1, 2, etc. Assuming the oscillators are in thermal equilibrium at temperature T, the partition function for single oscillator, okay, so this is for partition function for single oscillator, is sum over V goes from 0 to infinity and e to the minus beta epsilon V. So this is the general expression for partition function, any partition function. Any partition function Q is the sum over n e to the minus beta n, en, okay, like this, okay. So for single harmonic oscillator or single oscillator, so you write Q is V sum over V goes from 0 to infinity e to the minus b epsilon V. Now we substitute the value of epsilon V from here. So we get e to the minus beta h nu e V plus half. So if we further simplify this one, we get e to the minus x by 2 by 1 minus x, where x is beta h nu e, okay. So this is very easy to understand this one, okay. So how we will get it? Okay, let's see. So here, okay, so if we consider x is beta h nu e, okay, so x is beta h nu e. Now if we expand this one, sum over q is your sum over v goes from 0 to infinity e to the minus beta h nu e v plus half. Now we put v equals to 0, okay, so v equals to 0 will give you e to the minus beta h nu by 2, plus if we put now v equals to 1, you get e to the minus 3 by 2 beta h nu e, and the next one, if we put v equals to 2, we get e to the minus 5 by 2 beta h nu, and so on, right. So if we take e to the minus beta h nu by 2 out, so we get 1 plus e to the minus beta h nu plus e to the minus 2 beta h nu plus like this, so on. So now if we consider e to the beta h nu is x, so this is 1 plus x square like this, so this is 1 by x when x is very, very small. So that's why we are getting this value, okay. So from there actually you can calculate, you can arrive at this expression. So the mean energy per oscillator. So in order to calculate mean energy, what we need to do, we need to differentiate this q or partition function with respect to beta, and we need to put a minus sign. So mean energy per oscillator will be del ln q by del beta. So if we do the differentiation, and then we arrive at the final expression of this one, h nu e by 2 plus h nu e beta h nu minus 1. Now we need to calculate heat capacity. So in order to calculate heat capacity, we need to again further differentiate u with respect to temperature, right. Now, okay, the first term above h nu by 2 is simply the 0 point energy. This is the 0 point energy. When v equals to 0, we get this expression. Using the fact that energy is an extensive property, the energy of the 3n oscillators in the 3n atom solid. So if we have 3n number of oscillator in n number of atomic solids. For n number of atomic solids, we have 3n number of oscillators. So you need to multiply this u by 3. So u is the total energy of the system. Okay, system means when you have 3n number of oscillators. Okay, this is for single oscillator. The small u is for single oscillator, energy of single oscillator, or capital U is the energy of 3n number of oscillators. So we get u here. Now if we differentiate this u with respect to temperature at constant volume, we get the heat capacity. So the heat capacity at constant volume is therefore Cv is del u by del T at constant V. So we need to differentiate u with respect to T at constant volume. So beta is nothing but 1 by T. Okay, I forgot to mention that. Okay, here beta. Okay, so beta will be, so beta is 1 by kBT. Okay, kB is the Boltzmann constant here. Okay, or kT here is 1 by kT. K is the Boltzmann constant. Okay, times absolute temperature. So we need to differentiate Cv with respect to Cv. In order to get Cv, we need to differentiate u with respect to T. So if we differentiate this one with respect to T, Okay, so we need to we are arrive at this expression. Okay, 3nk x raised to the 2 e to the x by e to the x minus 1 raised to the 2, where x is h nu e by kt, where now we consider h nu e by k is another constant theta e is called Einstein temperature. Okay, so it has unit of temperature. So theta e is called the Einstein temperature, which is different for each solid and reflects the rigidity of the lattice. So theta e is depends on, you see, h is constant, k is constant. So theta e depends only on nu e. So nu e is different for different solids, right? So it depends on the type of or the type of solid we are considering, and it reflects the rigidity of the lattice. And this theta e, it has unit of absolute temperature, because x is unitless quantity, there is no unit of x. So theta e by t has to be unitless or no unit. Okay, so that's why theta e has unit of temperature. So at the high temperature limit, when t is very greater than theta e, or x is much lower than t, so when t is very higher than xc, so x value of x is much lower than 1. Okay, so the Einstein heat capacity reduces to Cv equals to 3n kb. Okay, so if we use this approximation here, implement this approximation, like when x is very small compared to 1, okay, then we get Cv is 3nk or nkb. Okay, that is your Dulong-Petit's law. Okay, so we get this one by setting that e to the x is 1 plus x in the denominator. Okay, in the denominator we are considering e to the x is 1 plus x here, and for numerator we consider e to the x is 1. Okay, so for denominator we are considering e to the x. Okay, e to the x equals to 1, and for this one denominator we consider e to the x is x plus 1 when x is very small. Okay. Okay, for this condition. So if we do it, if you see that, okay, denominator we get x to x square, numerator we have x square, they cancel each other, so you get 3n kb. Okay, 3n kb means Dulong-Petit's law. So when temperature is quite high compared to theta e, okay, then this Einstein heat capacity of solid reduces to Dulong-Petit's law. Okay, but but at the low temperature, when t is very small compared to theta e, means x is very large, Cv goes to 0, because we can now, x is very high, so in comparison to e to the x minus, so e to the x 1 we can neglect, so we get e to the minus x here, and e to the minus x raised to the 2, so overall you get e to the minus x in the numerator. So we in the numerator we will have Cv is 3n kb x square e to the minus x. Okay, since e to the minus x decreases rapidly with x compared to x square, so we get Cv goes to 0. Okay, so at low temperature, means when t is much lower than theta e, Cv goes to 0 as t goes to 0 as required by the third law of thermodynamics. This is proved by setting e to the x minus 1 is e to the x in the denominator. Okay, for large x. Next we discuss Debye's theory of heat capacities. So Debye refined Einstein model by considering the vibrations in solid as 3n coupled normal modes, each representing an independent harmonic oscillator with its own frequency. For low frequency vibrations, where the wavelength is much larger than the atomic spacing, right, the crystal can be treated as a continuous elastic medium rather than a collection of discrete atoms. In this regime, the vibrations correspond to standing waves within the medium, and the allowed normal modes represent the frequencies of these standing elastic waves. So Debye derived an expression for the number of modes with frequency varying between nu plus d nu in such a medium. So g nu d nu gives equals to your 4 pi v square times nu by v to raised to the 3 nu times d nu. So we get alpha nu square dv here, okay, d nu. Okay, so where v is the crystal volume and nu v is the propagation of the velocity of the wave here. As discussed earlier, this relation is only valid for low frequency vibration of crystal. Debye used the approximation to all frequencies and introduced a maximum frequency nu d known as Debye frequency. Like nu e was the Einstein frequency, here nu d is the Debye frequency, chosen that the total number of vibrational modes are 3n. That is integration 0 to nu d, g nu d nu gives 3n. The Debye frequency corresponds to lambda equals to 2a when the neighboring atoms vibrate in antiphase with each other. With approximation, internal energy is calculated by integrating over all frequencies and heat capacity is calculated by using this one. So we know this is the expression for Cv. Cv is del u by del t at constant V. So the resulting expression will be Cv will be, so if we if we further carry out, we arrive at this expression. So derivation is quite complicated, so I am just skipping that. So Cv is 3n kb, 3 by x to the xd to raised to the 3 and 0 to limit integration 0 to xd, x4 e to the x, dx by e to the x minus 1 raised to the 2, where x is h nu by k d kt. So here xd is h nu d by ktd, and we can, like before, h nu d by k we consider theta d, where theta d is the Debye temperature. Like Einstein temperature, theta d is the Debye temperature. So Debye heat capacity only dependent on Debye temperature theta d. So case 1 at high temperature, so at high temperature Debye theory also reproduce the Dulong-Petit's law. Let's see. So at high temperature, when T is much greater than theta d by T, theta d, so xd is much lower than 1 and x is very low, less than 1. So the integration, this integration here 0 to xd x4 e to the x dx by e to the x minus 1 will be reduced to x squared dx, right? So if we do this integration, we get x d raised to the 3 by 3, so we get 1 by 3 theta d by t raised to the 3. So if we substitute this one in Cv expression here, we get 3nk, 3 by xd t raised to the 3 times xd raised to the 3 by 3. So we get 3n kb. So this is nothing but your Dulong-Petit's law, as we discussed before. But at low temperature, when T is much lower than theta d, so xd is much greater than 1, so and x is very greater than 1, and integrand tends towards 0 rapidly for large x. So we can make upper limit infinity here, right, and turn the integral into standard integral. So this is a standard integral. So if we further carry out this one, we get 12 by 5 pi to the 4 nk by t by theta d raised to the 3. So we can see that Debye heat capacity decreases as T3 at low temperatures in agreement with the experimental observation. So this is known as T3 law. Okay, so according to Debye, Cv decreases with T3 at low temperature. So at low temperature, so what is the take away message? So Dulong-Petit's law, according to Dulong-Petit's law, okay, Cv is 3 ANR, right, according to Dulong-Petit's law, or for 1 mole means when n equals to 1, Cv is 3R, right, or you can write Cvm, molar heat capacity. This is according to Dulong-Petit's law. This is constant. There is no variation of Cv with temperature. According to Einstein theory, Cv is 3nr when T is much greater than theta I, Einstein temperature, right? When temperature is quite high. But Cv goes to 0 when T goes to 0 as Cv Cv is proportional to e to the minus e to the minus t. Okay, so not e to the minus, what was the value? It was e to the minus yes. So e to the x it was there. Okay, so you get so you get e to the theta e by t. So it goes like e to the minus x. Okay, you can say get e to the minus x. Okay, so it goes to 0 very rapidly. Okay, very rapid decay. Very rapid decay. It was like e to the minus theta e by t. It was okay. So when t goes to 0, it e to the minus x or e to the minus theta e by t. So according to Einstein's theory, yes, Cv goes to 0 when t goes to 0, but it decreases very rapidly. Whereas according to Debye theory, so Cv is 3 nr when T is much greater than theta d, right, Debye temperature. But Cv goes to 0 when T goes to 0, but here Cv is proportional to T raised to the 3. Okay. So, and experiment says, according to experiment, okay, Cv is proportional to T3 at low temperature limit. Okay. So Dulong-Petit's law was modified by Einstein theory, and then Einstein's theory further modified by Debye theory. So Einstein theory partially proved that okay, so Cv goes to 0 when T goes to 0, but according to Einstein's theory, Cv goes to 0 when T goes to 0, but the decay of this Cv with temperature was quite rapid because it was an exponential decay here. But according to Debye theory, okay, Cv goes to 0 when T goes to 0, but Cv is proportional to T to the 3. So its decay is much slower, okay, and it matches with the experiment. Now we discuss some problems here. Okay, the first problem is aluminium, atomic mass is 27 gram per mole, forms FCC crystal lattice. Calculate the number of unit cell in 8.1 gram of aluminium. Okay, so the number of moles of aluminium here is is 8.1 by 27. Okay, so this is the number of moles because 8.1 gram and the atomic mass is 27. Okay, so number of atoms of aluminium in 8.1 gram. So this is the number of moles times Avogadro number. So 8.1 by 27 times Na. This is the number of atoms, right, of aluminium in 8.1 gram. So we can write 8.1 by 27. Avogadro number is 6.022 times 10 to the 23. Okay. So what we need to consider, FCC crystal lattice, right? As the crystal is FCC, so number of atoms of one unit cell we just discussed is 4, right? In one unit cell we have 4 number of atoms. So number of unit cells will be 8.1 by 27 times 6.022 times 10 to the 23 by 4, right? So you get 4.5 times 10 to the